Hi, this is Quiz6. Okay, so we have this function in number 1, which I guess I will write out even though you're looking at it probably. F of x is defined in pieces. So the first part is x squared minus x divided by x squared minus 1. But that's if x is not 1. Which makes sense because you can't plug 1 into this function, so you don't want it defined in that case. But then this function happens to be defined as 1 if x equals 1. So in some sense, well, in a real sense, the domain of this function is now all real numbers, because if x is anything other than 1, you can plug it in here. If x is 1, you can plug it in here. Oh, actually, that's not true. The domain is not all real numbers because I can't plug -1 in here. So actually, it might be useful to record this. The domain is all reals except -1. Okay, so that's the function, and we're supposed to find out where it's discontinuous, or explain why it's discontinuous at 1, and sketch a graph. Well, to be continuous at 1 means that the limit of the function at 1 would agree with the value of the function at 1. Well, the value of the function at 1 is 1. That's because that's what it says right there. If x equals 1, the y value, f of x, is 1. Okay, so that's the value of the function, the y value of the function. What's the limit? What is the limit as x approaches 1 of this function? Well, to calculate that limit, I have to calculate the limit of that mess. But this is a 0 over 0 bad news situation. If you plug in 1, you get 0 on top, 0 on the bottom. So I have to do an algebra trick. Well, that's not too hard in this case because I can factor that numerator pretty easily, x times x minus 1. And the denominator also factors x minus 1, x plus 1. So you can see that those guys are going to cancel, and this thing, as x gets close to 1, gets close to 1 over 1 plus 1. So the limit of this function is 1/2, but the value of the function is 1. So the limit and the y value disagree, and so this function is discontinuous. So to have continuity, the limit of the function at the point must equal the value of the function at the point. So since this doesn't happen, this function is discontinuous. What does the graph of this function look like? Well, as long as x is not equal to 1, we're really looking at x over x plus 1. Now, I don't really think that you have enough tools right now to get a good idea what this looks like. I expected you to just go to Maple or a graphing calculator or a website like Wolfram Alpha and just type this in and get the graph of it. But we can get a good idea what it looks like just by thinking about it. We know that at x equal to -1 now, there's got to be bad news because, well, a 0 in the denominator and -1 in the numerator. So it's going to blow up at -1. We already knew that -1 was not in the domain, but we can tell that it's an asymptote. Then, when x equals 0, we can see that we're going to go through this point. And the limit as x approaches 1 is 1/2. So there's a hole right here at 1/2. But the y value of the function, for no apparent reason, is 1 at x equal to 1. So that much I know. And if we think about it a little bit more, we can see that with what we know right now, as x gets large, the limit of this thing is approaching 1. So 1 is up here. I'll draw it as a dotted line, but it will be a horizontal asymptote as x gets large. So it's approaching it. It's going to look like this. It's going to have a hole in it, and then it's just going to get closer and closer and closer to that value of 1. And then from here, I can pretty much tell what's going to happen when x is negative. In this part, it's going to be asymptotic down here to the line x equals -1. And then when x is bigger negative, like -2, -3, both numerator and denominator are negative, so the result will be positive. And we're going to have a limit of 1 as x approaches negative infinity. So we really will have an asymptote out here as well, and it'll blow up there. So we have this vertical asymptote here to which the function is approaching. So that's really the graph. The important thing for us right now is the discontinuity at 1 is a removable discontinuity, because we could redefine f of 1 to be 1/2, and then this function would be perfectly continuous, except of course where it blows up at -1. Okay, so that's problem number 1. Number 2 says find where this function is discontinuous. This function, which is x plus 1, or 1 over x, or square root of x minus 3. Well, rather than write all that over again, you can look at it, but these are 3 functions that are pasted together or sewn together. X plus 1, 1 over x, square root of x minus 3. Each one of those is a continuous function by itself. So the only way it's going to be discontinuous is at the seams, at the places where you're sewing it together. So what we have to do is check out what happens at a equal to 1. We have to check out what happens at a equal to 3. And that's about it. So the way to do this is to check the limit as x approaches each of these numbers from both sides. So what's the limit as x approaches 1 from the negative side of our function? In this case, what we're dealing with is as x approaches 1 from the negative side, x will be less than 1. And so you're going to use that first formula, which is instead of f of x, you just replace it by x plus 1. And as x gets close to 1, then this thing's going to approach 2. I did that right? Okay, what happens if you think about the limit as x approaches 1 from the other side, that is from the positive side, where x is bigger than 1? Then you have to use the other formula for f of x, which is 1 over x. So you're taking the limit of 1 over x as x gets close to 1. This time the answer is obviously 1. So the limit from the left is 2, the limit from the right is 1. So yes, this function is discontinuous at 1. So not continuous. Now we have to do the same thing at 3. What's the limit as x approaches 3 from the left? As you approach 3 from the left, this function means x approaching 3 from the left means that x is less than 3. So we have to use the middle formula. So again, we're looking at 1 over x. So the limit as x approaches 3 this time is 1/3. Looking at the right, the limit as x approaches 3 from the right of this function means x is bigger than 3. So we have to use the formula square root of x minus 3. So you think of x getting close to 3. Well, that means that this is going to be 0. 3 minus 3. So the limit from the left is 1/3. The limit from the right is 0. So this function is also discontinuous at a equal to 3. So it's not continuous at either of those places. However, if you look carefully, there's now it's not on the screen here, but you have to look at your function carefully. It says x less than or equal to 1, you're getting the y value x plus 1. So what that means is that as x gets close to 1 from the left, which is what we have here, the y value is 2, or the limit is 2, but the y value is 2 also because for x equal to 1, you're allowed to plug in 1 and you get 1 plus 1 is 2. So the limit of 2 matches the value of the function at 1. So this function is continuous at 1 from the left. Now don't confuse this, please. I didn't change my mind. This function is not continuous at 1, period. But if you're only looking from the left, it is continuous at 1 from the left. It's not continuous from the right because the limit from the right would be equal to 1, but the value of the function is 1 plus 1, which is 2. So let me write down what I'm saying here. F of 1 is equal to 2 for this function, which matches the limit. While we're at it, let's see what f of 3 is. According to the definition, we're allowed to plug in 3 in the third formula, which would be the square root of x minus 3, so 3 minus 3. So f of 3 is 0, which matches the limit from the right. So this function is continuous at 3 from the right. It's still discontinuous at 3, but the limit from the right matches the value of the function from the right. So that takes care of number 2. And now we get to number 3. A lot of people had trouble with this, partly because they never learned what the intermediate value theorem says. And that's hard for me to understand because the intermediate value theorem is so easy, so intuitive. It just says a continuous function can't go from here to there without going through every possible y value. And the most useful thing about this is 0 can be one of those y values. So if you happen to have a function that's negative somewhere and positive somewhere else, then it has to go through 0, somewhere in between, which means that your function at this particular value, whatever it is, c, let's say, would be 0. So somewhere between the beginning and the end, the negative point and the positive point, you've got to cross 0. So if you've got this function, or not, excuse me, you've got this equation, cube root of x equals 1 minus x, and you're looking for a root, a solution, on the interval from 0 to 1, then make a function out of it. Make f of x, you can say let f of x equal the difference of these two. So go from right to left, it doesn't matter, 1 minus x minus the cube root of x. This is a function. It's not only a function, it's a continuous function. Continuous on the entire interval, on the whole real line, in fact. Notice that f of 0 is 1 minus 0 minus 0 equals 1. F of 1 is 1 minus 1 minus the cube root of 1, which is also 1, which is negative 1. So the picture here is that at 0, you're getting a value of 1. At 1, you're getting a value of negative 1. So this function, f, which is this complicated thing, I don't want to graph it, I don't have to. It's continuous and it goes from here to here somehow. Well, it's got to cross 0 somewhere, I don't know where, but wherever it crosses 0, the intermediate value theorem, in fact, guarantees. So by the intermediate value theorem, there is a number c between 0 and 1 such that f of c equals 0. There's got to be a place between this x value and this x value where the function crosses 0. I don't know where that is, but it's guaranteed by the intermediate value theorem. And that means that at this number, if you plug that number in here, you're going to get 0. So f of c equals 0, but f of c is 1 minus c minus the cube root of c. And so what that means is, if you bring everything to one side, right, because you can toss the c and the cube root of c over here, then c plus cube root of c equals 1, and there's your solution. Oops, I wrote it differently. Let's try that again. I want to match this. So the cube root of c I'll toss to the left. So that means cube root of c equals 1 minus c. And that's the solution. C solves this equation because c made this function equal to 0. So that's a standard trick. We always do this. If you're trying to solve an equation, you throw everything to one side and make a function out of it, and you look for a zero, a crossing point, an x-intercept for this function. And you try to pull the intermediate value theorem out, because the intermediate value theorem guarantees you a zero if you can only find a positive and a negative value. Okay? And that's quiz 6.